So I'm so happy to introduce Caslav Brukner, a long-time colleague and friend and mentor. I met him in Imperial College the first time. I went as a postdoc. He's a visiting fellow at HKIAS. He's a professor in the University of Vienna and the scientific director of IQOQI, the famous institute. I mentioned Heilinger. So you know the Nobel laureate Heilinger's institute, so he's kind of a boss. So he has contributed many results to the foundations of quantum mechanics. And recently he's been working a lot on quantum gravity, space-time, but from a different approach. So many approaches are very mathematical. But Caslav is coming from a more operational quantum information science. If I may call it maybe Einsteinian, like thought experiments and things that are connected to something you could test. So today he's going to tell us about work on what happens if a gravitational object is in a quantum superposition.
One point. It's scientific director. It's not an administrative position. So it's like kind of a professor that corresponds to the institutes. But he used to be an boss. So let me start by thanking also Professor Lang and also Oscar for arranging this visit and giving me the opportunity to spend a couple of days. It was very intense and we had all the discussions, and I hope we will continue this in the future. And indeed, today I want to tell you something about our recent interest, which is at the intersection between quantum information and space-time physics. And as Oscar mentioned, it will be particularly the problem of how we should describe the physics in a vicinity of an object that gravitates and fits in a superposition of different positions. And this has been done together with two of my PhD students. This is Anna-Katrina Victoria Kabel, and Esteban Castro, who was a PhD student in our group and now is independent researcher. And so let me start then with the outline of my talk. So the question that I want to introduce, or the notion that I want to introduce first is the reference. And we all know intuitively what it is, but I want to remind you of that, and then to extend this to so-called quantum reference. And then I want to make use of this reference frame to introduce something which is superposition of classical transformation, classical symmetries. We all know what is symmetry under translation. But I want to say that this notion can be generalized in quantum physics, and that is a useful generalization. And then I want to go to the particular problem that has been mentioned and apply this in some typical quantum gravity scenarios in low energy. And finally, I want to conclude. So here is in Wikipedia the definition of the reference frame. That's an absolute coordinate system whose origin, orientation, and scale are specified by a set of reference points, which can be understood very abstractly, like geometric points, but they can also be understood physically. For example, if we assign coordinates with respect to some physical object as the origin of this coordinate system. And that's exactly what I want to propose. So here is a picture of reference frames. Let's think about two possible reference frames, origins of the reference frames. And then there is a system which could be a classical quantum system. And we want to specify the distance with respect to this reference frames. Well, these all reference frames here picture are physical systems, and all the physically meaningful statements about positions of this object, which is some kind of a wave packet, can be made with regard to these physical systems. And for example, we can say, well, the system is 10 meters away from the reference frame on the left-hand side, or the free is 30 meters away from this reference frame. So all the statements are with respect to other physical systems. Okay, so if this is so, we can also think about the physical systems, knowing the physical systems undergo certain dynamical laws, part of physics. We can think about quantum reference frames. These are exactly the same systems that we use in our everyday practice as a physical system, but with an additional feature that we can assign quantum properties. So if you want, it's like a cartoon, but you can think about one of those reference frames to be in subspatial superposition. Then we can ask ourselves, well, how will then other objects look like if I'm here in this reference frame on the left-hand side, or the right-hand side? I'm not sure how this, I have a little bit problems to get used on that, but it's fine, okay. So, in particular, we can think about the following question. If we talk about symmetries and the change of the reference frame, then we can also ask ourselves, what if these reference frames are quantum reference frames? And how we will change the description from one such reference frame to another? Does the physics change? Or there are some symmetries? Okay. So these are kind of the questions I want to pose. And we are not first to think about quantum reference frames as the notions that has started back in a long time ago in '84 by Brukner. But then there are many different things like quantum reference frames and quantum information by Rudolf Speckens, and all many more recent papers by different authors, among them maybe by Philip Kern, maybe you have seen. What I would like to concentrate myself today is this 2019 papers in building up upon that, particularly for the problem that I described previously. So what are reference frames good for in general? Well, sometimes we want to describe the physics from suitably chosen reference. Usually the physics doesn't depend on the choice of reference frame, the coordinates. But then in some of the coordinates or in some reference frame, physics look simpler. For example, in the rest frame, there is no many dynamical degrees of freedom. We sometimes choose rest frame to describe physics. So it's useful, it's simplified description. And the second, maybe more fundamental feature is exactly what I said, that we believe that the dynamical form of physical laws does not depend on the choice of the reference frame. So sometimes even this is a guiding principle to discover new physical laws. Because we say, oh, the physical laws should be invariant, should not change their form under this and that transformation, translations, rotations, age symmetries, and so on. And so if we are able to extend the notion of the transformations from classical reference frame to quantum, maybe we will stumble into something which is a more general physical law, a more general group of transformations. And then we want to find such laws. So let me give an example. That's an example. What I see here is a quantum system. It's a free particle seen from two reference frames. And we know that, that one reference frame with respect to another is translated by a fixed amount, x0. And now we ask ourselves, if we have a free particle in form of the Schrödinger equation to describe this system in the first reference, how does this dynamical law look like in another reference frame, which is transformed the old reference, the new reference? And in this case, this is the same physical law do not depend on the choice of the reference frame. And the combination and the particular transformation connecting the two descriptions is given by these translations with a P, which is a generator of translation, momentum, and a parameter X. And that's an example of what we call covariance dynamic force and change of reference. Now, the same could be also done boosts. I will not later on use the boosts, but I mentioned them here. The only difference between the two cases is the transformation that transforms the state from one reference frame to another is given by generator of the boosts, which is given by this PT minus NX. I think that I will take this because it has some inertia here. So you see that the generator is a little bit different, and by the parameter of the transformation is the relative velocity to reference frames. Okay, now in most general transformation between the reference frames, which could be even time dependent with some transformation S, the Hamiltonian physics will change from one reference frame to another. We had previously cases of free particle which doesn't change, but in general, Hamiltonian can change. Then, of course, the question is how we define the symmetry. We say that the symmetry is in that case when the original and transformed Hamiltonians have the same function. So if these are the same Hamiltonians, then it's the same differential equation describing the dynamics of reference frames, and that's what is the symmetry of the problem, and that's how we believe the fundamental physicals look like. So that's all about some kind of smooth introduction of things that you probably already know. And the next I want to go into describing now quantum reference frames. Once more, I start from a situation which is a classical situation. I have three objects, of which two of them will be all in the reference frame. That's the blue object at the beginning. This blue particle will be a reference frame, with respect to which I will define the distance of the other two objects. And then there is an orange particle, which will be the new reference frame. And after transformation, I will choose this orange particle as the origin of the new reference frame.
When you say reference frame, you mean the origin of the reference.
I think the origin of the reference frame, and you can think then maybe this origin is extending, there is a net such that I can count the distance of the first and the second particle. So there are three particles, of which two of them will take their own reference frame, and the gray one is basically the one which is not a reference frame, it's an object of observations. And now what we suggested back in 2019 is to keep the same structure, just to add to the positions X. Treat them as a localized quantum objects. And then the question is how we can go from this set of observations on the left-hand side, where these values can be arbitrary, to another set of observations. What is the law of transforming these coordinates? And in order to look at this, I want to introduce a little bit of handy notation. So when I say there is a state A, B, C, and then a superscript C, that means there's a state of A and B, C in the reference frame C. And there is this kind of a fixed position, which is always the origin. It's not really a dynamic field freedom because C is a position 0 always. So really what matters here are A and B. And when we transform it in a new reference frame, all what matters are actually B and C, where A is always 0. And now we ask ourselves, what is the transformation between this set of vectors and the other one? And so in order to describe this, I will decompose this transformation into two parts. The one which concerns the B particle, we see that there is a relative distance between B and E. And this relative distance can be obtained from the previous distance by applying, of course, general transformation or translation or shift in space by the generator, which is meant to move B. And how much we shift depends where A is, because it's relative to A. And then there is another part of this transformation, which concerns just swapping between blue and orange reference frame. Then in the beginning, we have 0 XA, and then have minus XA 0. So what this transformation does is what we call parity swap. It first mirror the position of A, and then swap the parties A and C. This really concerns just this part of the transformation, C and A part. And altogether, these two transformations can be written in a condensed way as a composition of these two parts. The first part being conditional translation of dB particle. You can think about this as read out first where A particle is, then you read out where the A particle push B particle corresponds. And this parity swap that concerns change of the origin in the reference. And this transformation is composition of two unitaries, so it's unique. So really, there is no loss of information going from one reference to another. Now I want to tell you why this is interesting. And here I take.
Sorry,
yes.
I just want to ask, there's something I didn't understand. Why is it not shifted on? Why there's a reflection thing, but it's if you think about this as being orientation of the increasing x, you see that if I'm now at that position, and I measure this distance left from me, then it will be minus xa. So I need this xa to change from minus xa. That's one thing. And I also need to change the roles of the CNA because what previously 0 was in C, yeah, 0 is in A. So it's really like this will be reflected into that from the origin.
How is it?
Yeah, go ahead.
I guess what Oscar means is that the unitary operator, like or the shift or the translational unitary operator consists of XA, PB, PA, and PC. So that translates all three of them.
Yeah, but these two are not important. Really, these two are not important because they are always zeros. So it's really what it makes is it transforms the Hilbert space of, let's say, A and B into the Hilbert space of C and D.
Which is order also important, right? So that you have already XA first, you have XA out, right? And then you switch. And then
Also, all what I need to say is that if you want this set of basis vectors to transform into that set of basis vector, that's the transformation. Mathematically, I try also to, with this what I explained, I try to argue why it's like that.
But if you still don't understand, I can write down another. I can write down another transformation which brings me from your side C to side A, like just by translating all three of them.
No, you can't. How would you do that?
Like I would write down a unitary operator like exponential. Instead of P hat of B, I would have P hat of A and P hat of C as well. In that case, I would translate all three of them
By which amount?
by the same amount XA.
But XA is an operator, right? Because this is something which depends on the type where the XA was before. Maybe this operator can be written in the other form.
Yeah, I know you've already said this, but can you say again what origin? The apply, which one's the mean?
The flag means that this is where the origin of the reference frame is, and you can think even that the origin is not important because it doesn't change. All the coordinates, it's like sitting in the here and looking at these two values. And then the next is sitting here and looking at these two values. So you first see that the Hilbert space change, because the Hilbert space of A and B changes in the Hilbert spaces of C and B. That's first. There are no, these are kind of dummy, this doesn't change anything. It's always 0 for no matter what XA and XB are here. And it's here is always 0 for no matter what that is. And so this doesn't really matter. I can delete this too, because they are not things that depend on it. Then I need to change from tensor product of the Hilbert space AB to the tensor products C and B. How do I do it? For example, like that. Here I have 0 and I have 0, but I can cut. It's just not important. This acts on A and B, and then transforms into a new Hilbert space, because you have swap between particle bits.
What does integral mean? Integral over x. What is the x? X is x.
Yes.
Every XA goes to minus.
Every XA goes to minus XA, no matter what XA.
Because the integral. The integral.
What is
variable? Oh,
It acts on a cat of XA. And then, of course, this is XA prime. This will be a direct delta. It will make of XA prime minus XA prime. I mean, it means the same as always.
Maybe what causes that confusion is that it's not DX8 rather than.
Yeah, it should be DXA, not XA. Yeah, it should be DXA.
And being a bit thick, but no, so if you just subtract XA from all of the ones that are left, then you get a minus XA 0.
Yes. But XA is not fixed. So you cannot imagine you say, oh, now I will subtract XA. You say, how large is XA? And you say XA is 5 meters. You say, okay, now I have a state where XA is 6 meters. So what do you do? Say, oh, now I want to subtract 6 meters. So you should have a unitary that doesn't depend on the state in which you apply. So that's why the unitary has an operator here. Read out what XA is. Whatever the XA is, then subtract XA. So maybe you gave an alternative unitary in an alternative way, written. And that's fine. If it is the same unitary, just written alternatively, fine. I don't know how would you write it exactly, because you want to say somehow you want to have here a generator which will be the sum of the all momentum, right? And here X.
Yeah, I guess I'm looking at like the top line there with the side C and side A, and so I could do that by shifting by like minus, let's say.
By minus XA.
So 0 goes to minus.
So how would you write it? How would you write it?
Something like your the integral there, and then you plus or sort of minus XA of that. Yeah, that's tricky because it's not the inverse equation.
I can say it's a classical background of the transformation.
So I have also I mean I want to keep also a right not to answer the question in order to go forward, but tell me what you said. There is a classical background.
Yeah, I mean, because you're talking about reference frame transformations, those ABC
Yes.
particles are referenced like more global. If you write out the quantum state, it's reference to a classical
Background. Just like in ordinary quantum mechanics. It's all like in ordinary quantum mechanics.
Yeah, this transformation is sort of like since we just have operate act on state.
Yes. It's like a controlled unitary. Controls, it's like a control unitary. I will give another way of writing this in short, in which is a control unitary.
So it's still, I think it's still like a classical. If you write out the whole one state, that's
Everything here is a class. I mean, I just put the cats. You can remove the cats. It's like they are localized states. I have not come to the point which I'm interested in.
okay.
But I think in response to this, thinking about, I mean, all what is important is that this is a unitary that responds to these bases, that basis. There is no doubt about that. Whether this can be written maybe the other way around is, I guess, would be. Okay, so let me now move on. And what I want to now look at is if the new reference frames, that's the thing that is not classical. It's really in a superposition statement. Here's an example that it's a superposition of two localized positions. And then apply our unitary transformation. What it comes out is basically that you transfer something which was superposition of this reference frame, then you localize yourself in this. And what you get is that two other systems are correlated, or even more precisely, entangled. And if you look at the states, you start with the state which is a superposition of the new reference frame and some arbitrary state of B. And when you apply the unitary, you get entanglement. Namely, this is maybe easy to also understand graphically, then you will say the state. Because if your reference frame was here, then you were closer to blue and further away from the gray one. So you're really closer and further away from the green. If you are in the dark orange, well, then you are further away from blue and closer to the gray. So it would be like that and that. So it's really like transforming the superposition of reference frame into entangled state of the rest. And that's what describes this as well. With respect to this, the C particle, the blue particle, will be either one or the other distance. But also correspondingly, you will shift the B particle for different amount depending on XA, which was the previous position of the reference frame. And so what you see here is that under quantum reference frame transformations, you can have dependence of superposition of entanglement. So there are notions that are relative to quantum reference. That was one example. I want to give you another example. There are like 4 different examples, but I will give you just 2 of them. We just discussed this one on the previous slide. So you had the old reference frame, and you have the new one in superposition and some arbitrary state of B. But when you jump on A, you get a super entanglement between C and B. Here is the opposite. In the old reference frame, the new one in B are entangled, so this is correlated, that is correlated. But you assume that the entanglement is a very special kind of entanglement, such that the relative distance between A and B is always L. So when you jump on A, fix you on A, B will be always on the same distance, will factors out, whereas the previous reference frame will become in superposition. So here is the inverse, like entanglement is formed in superposition. Okay, so what I want to say, and maybe this helps as well, another way of writing this transformation is really that this part is nothing else than the controlled unitary, because you can expand the X operator in the eigenspace. And so it will look like that. And then if you have this control on the state of A, you apply the spatial shift of the B part. And the first part is just the text as we used it before. In a similar form, and I will not go into details, there are other papers about that, you can extend the Galilean boosts. That's again a control of the boosting the P particle. How much we boost? We boost for the velocity of A. So you first read out not the position of A here, and they're shifting in space. You read out what is momentum or velocity of A particle, then you boost for this velocity of A particle, the B particle. Then you have also some swap, but not about X, but about velocity. And there is also a relativistic version of that, the Lorentz boost. I'm not going to be into that, but generally there is a paper which does this for any locally compact Lie group, in which you have you read out whatever the element of the group transformation for A particle, quantumly controlled change to B particle. Now I want to use this for something which is a typical low energy quantum gravity situation, which perhaps in 10 years' time, I believe in Marcus Aspenberg, will be maybe reachable or within the reach of the of technology.
Is there I really that's super interesting, but I'm really lost in this.
Yes, yes.
So I understand that this will give for each X, so look at translations, for example.
Yes.
Each X, there will be e to the I or h bar x a p hat. So it's a different shift for every X.
Yes.
For every X a. What was the reason
For that?
Yeah.
Because the X, so this is the moment that, so the classical transformation is such that this is a particle. Okay, and then you shift all particles for the same part, for the same amount. But here we say, look, but the particle is not a fixed mode. It's not a fixed, it's a superposition. So when I say I'm on the path, this from the original reference frame is delocalized. It's not delocalized. So I have to first read out where the particle is, even if it is in a superposition, and then shift the rest. And then, I mean, this, when I say B particle, it could be very complex, it could be all the universe, except the last reference frame, in which the relation between the new and old reference frame is very small.
So that you're moving the origin from C to A.
I'm moving the origin from C to A.
I want to be able to
I want to do that when it's position, I want to go back. Sorry, no, not forward. It's really this, if you want, situation that I'm moving reference frame from A to C. So the C, from C to A. So from point of view of A is localized, it's a 0 point. And so how I do it, I first read out where it is. If it is here, then I shift this for a different amount than as compared to another position. And that's why I have a quantum control shift, reading out where A is corresponding to shift. This could be very large system and composite system B. So it's very important because if we don't have a feeling for this transformation, we will not be able to make the next step. And next step is truly just applying this to a specific case of interest. And the specific case of interest is depicted on the left-hand side. Of course, it's a cartoon. I could amplify the situation such that you have a very large system that is put in a superposition. And then you have another system that we want to understand how this system evolved in the gravitational field of produced by a source in a superposition, gravitational source in a superposition. And I would say there are many proposals how to attack this problem. There are no experiments thus far. And we may say that it's a part of, let's say, unknown physics. And then there are different approaches. Some people would say, well, large mass would differ here. Why? Because there's a collapse model, here the innovator of Penrose's model. The other people will say, no, coherence is preserved. You maybe get evolution, unitary evolution of that and so on. But what I want to propose here is not to follow any of them, but to assume certain principal symmetry principle, namely that the physical laws are independent of the choice of the reference frames, which we use usually when the reference frames are classical, but here I want to extend this to quantum reference frames. And so I would say that there is a particular choice of the quantum reference frame, namely exactly the one in which we sit at a mass, large mass, and then the other things appear to correspond to this to be in superposition. And then to solve the problem here in this reference frame, because we know how to solve this. This is a well-defined space time, a well-defined gravitational field, and only the particle is in this position. So it's conventional physics. In a high energy regime, we might need to use quantum field theory, and because this time it's an easy theory to grasp and to use. But nevertheless, it's part of what is more conventional. And this is all based on idea again of a covariance of dynamical laws. It doesn't depend which reference frame I use, the physical laws remain the same. We call this extended symmetry principle, and now I show you on a simple side, in my opinion, quantum gravity scenario that probably is the one that will be first also measured. So what I have here is exactly three systems, like I had in the previous abstract introduction of quantum reference frames. I have the old reference frame. This was in our previous slide C. That's some observer. Then we have the new reference frame that was A system. Here is M, like a mass. And then I have this B object in the previous slides that will be system S. So that's the initial situation, and I want to solve this. I say, okay, I don't know how. But what I would suggest to go with our reference frame transformation from the reference frame R to reference frame M, and then the situation is different because now M is localized and two other things are entangled. Now I know how to do it. I will solve this problem. Eventually, I will get that the system falls down towards the mass in a superposition of two geodesics. And then I will go back with the reverse transformation, the solution. I will say, okay, that's diagram commutes, and that is the solution of the previous. Okay, so let's do it. Like, it's really a repetition of what we have done in the abstract way, just the indices has changed. So I have the new reference frame in this position. And then I go into new reference frame. So I change this superposition into entanglement. Now mass is localized, but all the reference frame and the system are entangled. And then I need to, this is now copied, this equation I need to solve this. There are many different ways to solve if you have such an object to solve this equation. And I here use the most simple one, which is based on the Law's approximation of so-called semi-classical approximation, to present Stodolsky, where you look at the localized wave packets as being really material points that follow the geodesics. But they are not localized in our case, they are just even entangled. And then there is also the accumulated phase, quantum phase that corresponds to the property time accumulated along one or the other path. So there is also not only these things follow geodesics, but also corresponding phases are accumulated. And now, if you do that, you have the solution, and then you can go of this solution back into initial reference frame. And in this initial reference frame, you will see what happens is that indeed the particle will get entangled with the position of the large mass, and the phases will be also accumulated the same phases as before. These are the phases. Now, this can be generalized into many masses in a superposition with some limitations. I don't want to go into that. maybe the point that I want to here make is that indeed when you transform under this quantum reference frame transformations, the S transformation, the form of the Hamiltonian remains the same, giving rise to a new symmetry of the problem, that this is a symmetry not only under classical but also quantum spatial translations. Now, it's not only that it works in Newtonian gravity. Here is an example. That's the smallest one that I want to, I mean, the simplest one after the Newtonian. The things are very similar as in the previous case, with an important difference that now what we consider as an object is not some structural particle that is free and falling. We imagine that there is a clock which is put in a trap in a fixed direction, a fixed, distance to the possible two positions of the mass. And now what we want to find out how this clock will tick. We know that time ticks slower closer to the larger mass. And so if this distance is not the same, the ticking rate will depend on some kind of quantum superposition, depending how close it is to the mass. But let's say we don't know how to solve this, because again, we are in some not well-defined space-time. So what we want to suggest is to use a quantum reference frame distribution again, localize ourselves at the mass, then solve this problem, which is a conventional problem in which there is one clock at superposition of two spatial distances, and then the ticking rate depends how far we are from the mass, and then go back. And this can be done in a very similar form like previously. We start with the same state. Okay, it's back. So we start with the same state. So this is state of mass, that's the position of the clock, but there is also some internal degree of the clock, because you need some degree of freedom to tick, not to be in energy eigenstates. For example, in a superposition of energy eigenstates such that it can tick, like for example, superposition of ground and excited state. And then again, we can repeat. I don't need to go into details. Going into the right-hand side picture in the new reference frame. In this new reference frame, the state becomes entangled between the position of the clock and the old reference frame. And then in this reference frame, we can, for example, that's one of the problems we did a long time ago, exactly the one clock in the position of two paths in a gravitational field. The ticking rate will depend on the position of the clock, and we can use this, compute then what will be the proper time along these for these two space-time trajectories, and this depends on position, relative position to the mass. So we can compute this and find out that well, the ticking rate will be entangled with the mass at the end, with certain phases that we can also form. And so, indeed, we can solve this problem again, also for the case where the mass is in superposition and the clock is localized. What we obtain, and I think I'm here at the end of my talk before the conclusions, is some effect which is very small effect. I imagine you have two large masses of 10 to minus 8 kilograms in superposition. You have a localized clock. Now, for the distances about 10 minus 5 meters, and for the duration of the experiment, 1 second, you get something that the uncertainty in the ticking rate is 10 to minus 32 seconds, or what we can measure now is 10 to minus 18 seconds. So it's a very tiny effect. But what I want to say is that still, this effect is many orders of magnitude closer than what people usually think that something interesting is happening at nighttime, which is 10 to minus 44 seconds. And also, I want to say that such an experiment, for me at least, would be a genuine proof of superposition of times. Because in no experiment, in a definite gravitational field, a clock that is localized can tick in a superposition of time. Because if the clock is localized and the gravitational field is well defined, the ticking rate is well defined. And so it cannot show superposition. Only it can show superposition when the clock is delocalized and the mass and the gravitational field is well defined, or here, the other way around, where the gravitational field is in a superposition and the clock is localized. And by proving these localizations, we can show that there is something which is genuinely where the time is not well defined. Of course, then one should look at other clocks, like in the spirit of GR, you can see that this effect does not depend on how we build up the clock. We say this is a universal feature, so it's not about the clock, but really about space now. Okay, and so let's go.
So I really like this idea of switching to reference frames. I think I understand that. But here I just got a little bit lost about what's the. I think you're making some kind of experimental prediction.
Yes, I'm taking here the experimental prediction. I put in some numbers and I say, okay, so can we prove? Can we prove the superposition of space? How hard is this? And what will be the minimum requirements? And so I'm leaving now this possibility of going from one reference frame to another. I'm just saying, okay, we know how to compute this. That's by switching different reference frames, how to calculate things. But now let's go to the lab and do this experiment. And then I prepare a large massive superposition, and I want to see when, which experimental conditions I can see that, for example, this clock is not ticking at the well-defined rate, meaning that if I repeat experiment, sometimes I see that it ticks according to one rate and the other according to the other rate. So there is some time difference that or time uncertainty of this clock, which will be induced by the fact that the clock is not always in a fixed space-time, fixed rotational. And then I see that this is a very hard problem experimentally. But still, I want to argue that it's easier than what people usually expect. Quantum gravity effect should kick in high energy. So I think there is a merit to it. It's very hard.
Why did you pick this L1?
It's something which is still very hard because it will be even harder. So
how would you?
So I was picking these numbers, but this number I didn't pick. I mean, computed, knowing that the best clocks will do 10 minus 18, 19, 20. So quite far.
What's the background of the, the Minkowski space or?
The background is not well defined.
Oh, in fact,
Superposition of two buckets.
It's the superposition of two vectors.
just two back. Okay.
Sorry?
There's no, so it's, you're imagining a massive house space. Or,
But then it will not be Minkowski anymore.
yeah. Oh,
And so what we mean is, so then we need to add some
You need to do it. You need to do it. I didn't want to do it, but for example, one thing is that which will be harder is that to prove entanglement, because ticking rate, not only the answer, ticking rate will be entangled. So how fast this clock will tick depends on where the mass is. And so the ticking rate or internal degree of freedom of the clock will be entangled in the position of the mass.
I guess I have one question is if this is like not in our space time experiment, or at least we need to add some
We are
actions.
outside this,
We are outside of this, so how the people will do it? Experiment. They will sit in their laboratory in the time space time, then they will have a heavy object put in the superposition of propositions. And then of course you have to be sensitive enough to measure the difference.
Yes, I mean, but this is different from this. I mean, must be the because this is imagining just the math to math in superposition.
And nothing else.
Yes.
No, you can think about, this is a more fundamental question. I made problems, but remember that when I was looking at this, I said that there are three systems. I mean, there was this R, that was the reference, old reference frame. So you can keep this old reference frame there as well. You can have a reference frame which is localized here. Why not? There's nothing which is wrong with this.
Okay. Okay.
I mean, there are maybe data factors out from this example.
I'm a bit uncertain how to measure this certainty because I think if the clock gets in a superposition of two time relations,
Yes.
I go and look at the clock, then I collapse it into one of it.
It's true.
So eventually I see one.
Yeah, no, okay, so this is the usual thing how you can prove superposition. You either measure in the superposition basis. The other thing is what Oscar asks, is that when you measure, and you can have such a sensitive clock that this time dilation of 10 to minus 3 seconds, 15 seconds, is one or the other orthogonal states. That's we don't have such clocks, but in principle. So when I measure, I really know is it one or the other ticking rate. But of course, this alone will not distinguish this from the mixture. So what you need is prove the entanglement. And this will prove that there is a coherent thing. Or to really be able to measure it with iteration in a superposition of these two states. And see, okay, this is neither one nor the other well defined by the superposition. Yes.
Instead of like testing gravity of the reaction again, I can also imagine like by preparing a superposition position of a charged particle and then like think of something that interacts electromagnetically. That it seems to me that this is like testing whether you can really superimpose something in position.
But I would say if the large mass is in superposition, we believe in what we know from GR, the gravitational field will be in superposition, and then the metric will be in a superposition as well. And what I want to say is that exactly by this example of the time, the rest of just the previous case where I have a structural particle, that even no matter how we measure the time, it will get entangled.
Yeah.
And so if you think about, and for me, it's really operational sense when Oscar said, what is time? Time is what clock shows for me.
Yeah, I understand. But like this is slightly different from what we mean by quantum gravity. Because here you have like instead of gravity itself, you have sources that are
Yes.
yeah.
Yeah.
You
It's
have
not very
superimposing. Yeah, exactly. That's what I mean here. It's not quantizing gravity, like you have superimposing your sources.
But this is more than superposing the sources, because it can be that when a source is in a superposition, the gravitational field of that source only can behave according to the average of the two states of the superposition. But that will not cause the entanglement that is proposed in this experiment. But then if the gravitational field gets also in a superposition and a joint superposition with the source, then it will cause the entanglement. So this is not testing gravitons, but also not simply superposing the source without the.
I think it's really now a matter of taste, and it's a matter of what we can do experimentally first. I think gravitons are far away. Ultimately, it will be a beautiful experiment to prove the gravitons, quantum, like a photon, quantum state. But still, I think there's something interesting that will be a fundamentally new state of space-time, because we will not be able to assign definite metrics to this space-time. And the proof of that is that no matter what clock you have a universal fact, the time ticking rate is not valid. This is not graviton. I agree, that's something which is, you can think about this one gravitational field as a constraint on the mass, where I move the mass, but yet it's not in classical state, what we will say. Okay, I think the next is something what Ali just mentioned, and this is, I want to compare models that obey this extended symmetry principle, namely models that obey symmetry under exchange of reference frame, with some other alternative model put forward sometimes in gravity community or people who are working on the internet. There are two of these models alternative. One is semi-classical, which is the far right side, where you think that gravity is sourced by the average, the gravity is average gravitational. It's all what's sourced by any configuration of matter. And then in the middle is the collapse models, where the superposition are caused to be destroyed by some not yet discovered mechanism, but really has to be, because you shouldn't have a superposition of large objects. And the last one is the one which obeys the symmetry. So let's go on the right hand side. What I want to argue that these two other models do not obey symmetry. And these two other models, physics is not the same as seen from different reference frames. Could be that it's like that. Maybe some reference frames, are more preferred. It's not the spirit of how we understand physics so far. So here is the semi-classical gravity. So look at this. What I see here is let's say a localized mass, and I put a small mass in superposition. Now in a semi-classical gravity, the gravity that this small particle will experience is something which is averaged over the position of the source. But the source is localized, so the average is the same as just like in this picture. Okay? And what will happen is that these two amplitudes, possible positions of the small particle, will move towards, attractive towards the large mass. So these two things will come together. Now the same situation I look from the other reference, from the reference frames of the small particle, which the big one is in superposition. Now right in the middle here, if I'm very precise, I succeed to break the electricity, right in the middle is gravitational field 0. So it will stay there. So you see that this situation, the seed from two different reference frames, results in two different effects. So this theory is non-symmetric under quantum reference frames change. Similar thing is in a collapse model. I again start with the same situation. Now in the collapse models, usually the small masses do not collapse. So you're having here coherence of things. But from the point of view of the small particle, the big ones in this reference frame, it has to collapse according to these things. And when it collapses, you lose the coherence. And only the last one, the one in which I calculate the things, is the one in which doesn't have the effect of attraction of the small and big is independently of the reference frame. And with this, I'm concluding. I mean, I was too long, but it was many questions. So I tried to argue that there is a way to treat reference frames as quantum systems, that if you do that, the superposition and entanglement are frame-dependent motions. Then I try to argue that one can generalize the symmetry principle to quantum reference frames, that this extends the possible set of operations, or transformations and symmetries, and use this to predict what will be the dynamics of pro-particle and time dilation in presence of gravitational source in superposition. And of course, more work should be done on understanding these experiments in principle, possible quantum general effects. So with this, I would like to thank you very much.
Very nice talk. So I'm not sure if I understand it correctly. For me, the transformation considered here is only the Galilean transformation.
What kind of transformation?
Galilean.
Galilean, yeah.
So-
Galilean here. Aha.
Is it possible to maybe generalize to reference frames which are only out now? So
There is works also for the Lorentz transformations. So here are just really, I don't know whether Galilean, because I didn't talk about boost, I didn't talk about Galilean boost, I talked about translation. I wouldn't say that this is necessarily non-relativistic, it's just translations. And as we see, for example, we can get gravitational time dilation because it depends only on the relative distance, this effect, but it's not necessarily non-relativistic. However, if you consider, for example, boosts, then you can have also quantum control Lorentz boost. And this we used in one Israel letters a couple of years ago to solve one open problem in quantum equation. This problem is, for example, how do you define spin of this? Because of spin gets entangled with momentum. Because this old paper by Perez, Scudo, and Anterlo saying that if you look only the spin, in the boost, sometimes you lose coherence in the spin. So you lose the qubit, like where the information is gone. So we use this to say that the way to solve this problem is to go into the rest frame of the particle. The rest frame is like a non-relativistic. Small, there is no movement. In the rest frame, we know how to define the spin. This is a Pauli matrix. Then we go back. And then we really see that you don't lose any, there is a one-to-one correspondence between the spin in non-relativistic case and the I know that I wasn't clear enough, but yes, there are works on Yes.
I can have a superposition of reference frames if I take quantum reference frame. And can I have interference of reference
It depends what you think. Once you is interference more than superposition, you mean that measure and see some effect. But you see that here the transformation between one and the other reference frame is unique. So whatever the state is, you will know one or the other. Maybe your question is more about what if I have some now measured in one reference frame? How does it look from the other reference frame? And this is a more subtle thing, and not many people look it up. And in our original paper, we have a situation in which we look at because interference effect, I understand, like kind of a measurement. So we have from the reference frame something what was measurement on this object. So we have some kind of pointer, we angle with this, so we model the measurement, usual method, like between. So that if you make a measurement on P in this reference frame, this is measurement involved. It's only what I can say.
Okay, so but then what I had in mind is if we take these three particles, maybe the next slide where there are more positions.
Yes.
And then if I take the first the particle A, which is the target reference frame,
Yes.
on the left hand side,
Yes.
and then if I let everything move towards the y-axis,
Yes.
So we've animated this slide and just move. Yes. And then I let the orange particle A go into some interferometer,
Okay.
where it splits. When it splits, then I get exactly this
Exactly.
scenario.
Yes.
From the reference frame A, it's the one to the right.
Yes. Yes.
But then it merges again.
Yes.
And as far as I understand from when it merged again, from the perspective of C, for example,
Yes.
A merged again. So A will have an interference, if it reaches some screen or something, A will have an interference.
Yes.
Then from the perspective of, now if I go to the perspective of A, which from C is interfering,
Yes.
now A is the one that's interfering, but is looking at the world. Will it see the world interfering, or will it see
I would say if you're now in this reference frame, you will see even huger entanglement. You will see something like very similar, like what I had later on. I didn't comment this, like something like okay, so something like that.
Hmm.
But it's inverted now. But what I want to say, you will have entanglement in many positions the previous one. So really like a continuous version of that, or not continuous, but exactly as the interference pattern. Because once you have a state in one reference frame, you already know it. You can dynamics you can do in any reference frame, but then you have one. You can always use the same.
So A that used to be an interference pattern with C, B, and C, they are an interference.
They are entangled.
They are entangled and
You have this pattern. Yes.
another question. Sorry, I mean, another question. Another question is so all this for free particles. Now, have you or anyone else considered any interaction scenario?
Well, first of all, this is spatially interacting. That we consider now between A and B, but and exactly because this gravitation interacts depends on the relative distance. It doesn't matter whether you make one or the other reference frame that are addressed to each other. Quantum control.
There's more to it because in your case, you take a probe and you consider that probe does not have a gravitational field.
Yes,
Yeah.
I understand what you said.
Now, if you have two big masses,
I think I haven't seen this. Yes, this is more dynamical in the sense that the mass is so large that there is no back direction, say on the mass from the probe particle. And if they are all, I haven't seen anything.
so my reference frame will be gravity. I think an easy way to implement this is to, when my reference frame is gravitating.
There are two things. Sorry, there are two things. One is that when you say that my reference frame, the original one, that's one generalization. The other generalization is that A dynamically changes as well. I put large mass, but A hasn't changed. The position of A hasn't changed. It's very simplified. So even there you can extend in both ways. Sorry.
Yes. Okay. Yeah, this is not what I had in mind. What I had in mind is both having gravitational field.
I understand.
And then now my reference frame will have a gravitational field, but this will be described as a background potential. Because you like to put a reference frame in a state 0. And if you want to keep this,
I honestly think I'm not sure. I'll now explain why. Because if this also sources gravity, when I go to that one, so I say, oh, now I make this gravitational field from that definite, I will still have the other one indefinite. So I'm again in this problem that I cannot. So this, what I want to say, this procedure doesn't work always. because there could be such superposition that there's no way to choose a reference frame in which the gravitational field will be. But it can be a guiding principle in the sense that if this can be done, that can be calculated in that way. But now, after you do this calculation, you will realize that what you have done is actually linearly superposed. So at some point, you don't need to do all of it. So I said, okay, if it's not definite, it's a superposition, then I just use it.
I really like the basic idea that you have a mass means position. Cases that scenario is the same under the reference frame. And the mass in one cases that is
There's this calculation of each of
Thank you so much.